Okay, so expected value, the expected value for a random variable, x is in here. So the mu stands for the average or the mean. Fancy E is the sum of. X is the payout. Doesn't always necessarily mean it's going to be money, but it's kind of just like the generic term we use for it. And then P of X is the probability of each payout. All right, so it costs $5 to play a game. You draw a card from a standard deck of cards. If you draw the ace of hearts, you win $100. All other aces win $10. All other hearts win $5. So what is the expected value of the game? So you have to pay in $5 to play, so we have to account for that as well. So when we're doing the payout for the ace of hearts, it says if you get the ace of hearts, you win $100, but you paid $5 to play, so we would do 100 minus 5 to get $95 would be the actual payout for what basically they would owe you. So it would be 100 minus 5, which would give you 95. The other aces said that you win $10, so it would be $10 minus the 5 that you paid to play. It'd be $5. If you get any other heart, you get $5. So it would be 5 minus the 5 you paid in. So they don't have to pay you anything. Or, well, basically you don't have to pay anything. And then all other cards, you get nothing, but you still paid 5 to play, so that ends up being -5. So then we have to find the probability of each. So with ace of hearts, there's only one of those in the entire 52 card deck, so the probability would be 1 out of 52. All other aces, well, there can only be 3 other ones, so that's 3 out of 52. Other hearts, there's 12 of those, so that's 12 out of 52. And then everything else, if we add those up, that's 16. So 52 minus 16 is 36, I think. So 36 out of 52 would be that probability. So we can't do the last column until we know our expected value. So we're going to add up all the expected values from using this formula. So it'll be payout times probability plus each one. So mu is equal to E of X, which is equal to, so the first payout is $95. So 95 times 1 over 52 plus 5 times 3 over 52 plus 0 times 12 over 52 plus -5 times 36 over 52. And if you were to type all that in and solve it out, it would be -$1.35. Phone charger? Yeah. Yeah, no, it's still in the thing. So to find the standard deviation, it's the payout minus this expected value, but it's going to end up being minus a negative, so we're going to be adding. So 95 minus negative, which I'm just going to go ahead and change it to plus. So plus 1.35 then 5 plus 1.35, 0 plus 1.35, and then negative 5 plus 1.35. So we could also do it where we didn't account for basically what you paid in, and we could still like solve it the same way. So we would have like 100 times 1 over 52 plus 10 times 3 over 52 plus 5 times 12 over 52 plus 0 times 36 over 52, and that would give you $3.65. And that tells you how much you expect to win on average. But if you account for the fact that you paid the $5 to play and we subtracted $5 from this, it'll give us the negative 135, negative $1.35. So if we didn't account for up here the payment of the $5 to enter the game, hold on, 265, 165, 65, negative 65, negative. Hold on, I may have the number multiplied wrong. No, it's 5.
It's 5?
Yeah. Apparently whoever was in the computer lab the other day heard y'all screaming about cookie points. I don't remember who it was, but it was funny. Because I don't think it's somebody that had me, and they were like, what's a cookie point? I was like... So this is what you would expect to win, but if you account for having to pay to play, you're actually losing money by playing most of the time. So on average, you expect to win $3.65, but since you paid $5, you actually lost $1.35. All right, so then the next question is, what is the standard deviation of the payouts? Remember, standard deviation is the square root of variance, so we're actually going to find variance first, and then we'll take the square root of it to get the standard deviation. I'm going to label this first. So still, X is your payout. Mu is your expected value. And then P of X is your probability of payout. So basically we have each of our standard deviations because that's the x minus mu. And then we're going to be squaring those values and then multiplying them by their probability to get variance. So we'll have variance is equal to 95 plus 1.35 squared times 1 over 52 plus 5 plus 1.35 squared times 3 over 52 plus it's 0 plus 1.35, so 1.35 squared times 12 over 52 plus, okay, well, didn't all fit, negative 5 plus 1.35 squared times 36 over 52 and so then once you type all that in, solve it, blah, blah, blah. Variance is equal to $190.08. And so then when we take the square root of that, to find the standard deviation, we get $13.79. And then a follow-up question that's not actually written on here, but that's something that's good to point out. Why is the standard deviation so much larger than the mean? And the answer to that would be because there is a lot of variation in payouts. Because you could pay out $95 or you could pay out nothing. So there's kind of a wide spread of options. All right, pick any card, any card. You draw a card from a deck. If you get a red card, you win nothing. You get a spade, you win $5. For any club, you win 10, plus an extra 20 for the ace of clubs. Create a probability model for the amount you win at this game. Huh? Okay, that's fine. Nothing. Huh? Gotta love it. Like, not me. Alright, so our payout for a red card is nothing. So it's just 0. And it doesn't say we have to pay anything in, so we don't have to subtract off anything this time. A spade is $5. A club that's not an ace is $10. An ace of clubs is 10 plus the extra 20, so it's $30. So the probability of those, the probability of a red card, well, it's half the card, so 26 out of 52. Or you can reduce it down to 1/2 to make things easier when you're actually solving it. A spade is 13 out of 52, which is 1/4. And I'm reducing those because it like makes them way simpler. If it's just like take out a 2 or something like that, a lot of times I won't reduce them, but you can if you just really want to. So then a club that's not an ace, that would be 12 out of 52. And an ace of clubs is 1 out of 52. So the expected amount that we win, it's just multiplying and adding together. So 0 times 1/2, which if you don't want to write the 0 terms, like when you know it's just going to come out to 0, you can skip that one. Plus 5 times 1/4, plus 10 times 12 out of 52, plus 30 times 1 out of 52. And if you multiply that out, we get $4.13. So how much would you be willing to pay to play this game based on that information?
How would I be willing to pay?
Yeah. Like, what do you think? I guess I should say, what would be a reasonable ask for you to think, oh, it's worth me playing this game? $5 and risk losing money? Okay. So you can make an argument for that. Mathematically, we would probably say anything less than $4.13, so that we guarantee we win something. Well, I say guarantee. Obviously, there's a chance you don't win anything.
Is that like an opinionated question?
Kinda. I mean, yes, it kind of is, but at the same time, it's also kind of like look at the math of it and see, like, if it was on the AP exam, they would want you to say anything less than $4.13 to guarantee you win something. But if you just wanted to chance your odds, and yeah, I mean, $5 could be reasonable. And I mean, even at $5, you're only losing like, what, 87 cents if you do that, so. So find the standard deviation of the amount you might win drawing a card. So it's going to be the payout minus the expected value squared times the probability. So I don't know why I made this space so small, but variance, we have to do that first and then take the square root of it. So 0 minus 4.13 squared times 1/2 plus 5 minus 4.13 squared times 1/4 plus 10 minus 4.13 squared times 12 out of 52 plus 30 minus 4.13 squared times 1 out of 52. So your variance would be equal to $29.54. So the standard deviation is just the square root of the $29.54, which comes out to be $5.44. So we'll stop there because we're basically out of time.